over to the cloud. And oh, it just did it. Okay, so we're recording now, it looks like. Cool. So I think we're about ready to get started. So thanks guys for coming out to this. I know oh, we got one more person. Andrea's here. Um, so I know that the quarter is getting along now, and a lot of people probably have midterms and stuff. So thanks for coming out despite this, and you know, coming to the 10 millionth Zoom thing that you've seen or whatever. So really appreciate that, guys. This stuff's really interesting stuff. It's a little bit more kind of involved than the past workshops we've done this quarter, but a lot of it is also non-technical, and we're talking about like satellites and some pretty basic concepts. So I think you guys will enjoy it. So um, I guess we'll start out with some brief backgrounds. So, Matthew, I'm going to turn it over to Matthew, and he's going to talk about what quantum computing is. Just kind of a little either refresher or introduction if any of you guys haven't seen it before. Um, good review either way. So, go ahead, Matthew.
Yep. Yeah. So let's talk about what is quantum computing. Well, you're all familiar with classical computing. Hopefully, I mean you're on this Zoom call. But the difference between quantum computing and classical computing is that quantum computing basically exploits quantum physics. So as we talked, there are a couple like really important properties, but they are essentially qubit, superposition, entanglement, and quantum measurement. And these three properties allow the amount of information that a quantum system can store in itself to be much larger than the amount of information that some regular classical bits can store. And mostly that is a function of superposition, essentially the qubits being able to be in a mixture of 0 and 1 states at the same time, and also entanglement, which is basically when two separate qubits can be in a very special kind of state where based on the state of one qubit after a measurement, you can predict the state of the other perfectly. And the phrase that comes up a lot is Einstein, when he learned about this, he called it spooky action at a distance, because if you think about the consequences of entanglement, then it is really surprising. It means that based on the state of one qubit that's like thousands of miles away from another one, you can actually predict the state of the other one, because that's what entanglement means. And these properties of superposition and entanglement allow you, if you write a very clever, a very special algorithm, allow you to get an enormous speed up for certain tasks. And algorithms that have been demonstrated include factoring prime numbers. This is really, or doing prime factorizations of numbers. It's a really famous example, Shor's algorithm. Also doing disordered searches, which is Grover's algorithm, and all sorts of different algorithms that usually take advantage of periodicity in a problem. If a problem has a natural period, then you can exploit that using the quantum properties of quantum computing. And then it also has some potential for like just simulating quantum physics, so quantum materials and that kind of thing. And this is really interesting for clean energy research. So for instance, for solar panels and optics and even transistors and stuff. So it's an interesting kind of field, and it has a lot of promise, and it's very complicated.
So, I'm actually going to talk about the BB84 protocol a little bit for you guys, because I think it's something that you can understand fairly easily with just your, just the background that you have already, and I think it really helps. I think it really helps with understanding why quantum communication and a quantum internet would be so effective. So we're just going to kind of talk about photon polarization real quick, because that's a really easy way to visualize this, right? We can almost not really have to do any math whatsoever, in fact. So I'll kind of show you guys how this works. So any of you guys know what photon polarization is? I think we've talked about it before in one of our meetings. But I was wondering if any of you guys kind of feel like you understand it. So don't all go at once. But yeah, no. If any of you guys want to try and explain it real quick, feel free. But it's all right if you don't want to. We're talking about polarization, right? So we have an electric field that is polarized. Anyone know what that means? So, sorry, I'll go over it. So we have an electric field, right? When we have a light wave. So in classical physics, we have, you know, um, an oscillation in the electric and the magnetic field. So if you've taken your physics classes, or even if you haven't, you might have heard this, right? We call electromagnetic radiation, those oscillations in those fields, right? So, for example, let's say we have an electric field, and we're going to imagine we're looking at this thing head on, right? So, we have electric field, we have electric field vectors, right? Oh, and I was annotating. There we go. So like if we're looking at a wave head on, right, we have that vector. It's going to start out small, right? And I guess I'll give you guys kind of a side view so you can kind of see what's happening here, right? A lot of you might have seen this kind of thing before, right? We have an electric field. It's increasing, right? And then it's decreasing, right? And it's oscillating like this, right? So if you look at this head on, you're going to see, right, you're going to see basically a line of electric field, right? It's going to be going up and down, right? We can also have different, so that's what we call a polarization, right? This is a vertically polarized electromagnetic wave, right? The electric field is oscillating in the vertical direction. We can also have a horizontally polarized electric field here, or a horizontally polarized electromagnetic radiation, right? So, and we can have anything in between, right? We can have diagonal polarization, right? We can have, anti-diagonal polarization. We have all different types of polarization here, right? If we take a polarizing filter, so if any of you guys have polarizing sunglasses, right? Those have polarizing filters in them. Those sunglasses are taking the all the photons that we have, and let's say we have photon 1 that's polarized like this, we have photon 2 that's polarized like this, photon 3 is polarized like this, photon 4 is polarized like this, for example, right? What this polarizing filter does, and let's say we're taking these photons and we're putting them through this filter, so we're taking light and we're filtering out polarization states here, right? So let's say this is a vertically polarizing filter. So, and now you guys can participate. Which of these 4 photons that I drew is going to pass through this filter completely unaffected? So it's a vertically polarizing filter. It filters out everything that's not vertically polarized, right? So that everything coming out of this will be vertically polarized. So which one on the left here, which one of these is going to go through without any resistance? And I haven't been checking the chat, so you guys might be answering there. Oop. Yeah, exactly. This second one right here, right? Okay, so you guys are getting it. Oops. Wow, it's not letting. I can't I can't move the chat around while I'm annotating. That's all right. So that's basically the intuition you need. It's like 90% of it, right? A vertically polarized photon is going to pass through this filter unattenuated. This horizontally polarized photon is going to completely get blocked, right? It's impossible for this photon to pass through. Now, it gets a little more complicated when we're dealing with diagonally polarized photons, right? Normally, if we had, diagonally polarized light, we would, this diagonally polarized light has a vertical and a horizontal component to it, right? So if we're passing it through that filter, we're just getting rid of this horizontal component and we're keeping the vertical component here, right? But we're dealing with one photon, right? So we can't get rid of the component of one photon, right? The photon is the indivisible unit of energy in light, right? So we can't take a photon and get rid of some of its energy. We can't get rid of the part of the electric field that is in the horizontal direction. So what happens with these with these diagonally polarized photons is, let's say we're at 45 degrees here, right? So exactly we have a 50-50 chance of that photon getting passed through, right? So these two diagonally, let's see, it's this one, right? These two diagonally polarized photons, they have a 50-50 chance of coming through. And when they get through, they're going to be vertically polarized. So that gives us something so that is actually a form of measurement, right? If we have photons in the, and then we're going to talk about basis, right? So if we have photons in the the xy, or the vertical horizontal basis here, right? Those photons are going to pass through. We're going to be basically performing a measurement on them, right? If they're we're going to find out if they're horizontally polarized, they're going to not get passed, right? They're going to be stopped, and if they're vertically polarized, they're going to go through, right? So we can apply, that's basically a measurement in the horizontal vertical basis, right? And then if, let's say, we pass diagonally polarized photons, are we going to get any information about these diagonally polarized photons when we pass them through? If they're all, let's say they're all at 45 degrees, are we going to get any information? There's a 50% chance it'll pass through, and then if it passes through, it's going to be vertically polarized. Do we have any information left about the polarization of that photon? So we don't, right? And that's really important. That's a big concept in quantum computing in general. Is that we have when we measure in one basis, right? We destroy information that is 45 degrees off from that basis, right? So we could also put this thing through a diagonally polarizing filter, right? That diagonally polarizing filter will destroy all the information about our vertical and horizontally polarized photons, right? So how do you guys doing? You guys have any questions, any clarification, anything like that? So hopefully I'm trying to break this down as much as I can, make this as simple as possible, because I think it gives you a really good intuition on this stuff. So next we're going to talk about, then I have to stop my annotation. So we're going to talk about the BB84 protocol, knowing that, right? So we have these states right here. We have this, we see a bunch of pluses and minuses and zeros, right? So we don't have to think about this too much. All we have to know is, let's say 0 and 1. So this is our Z basis. Let's say this Z basis is putting something through a vertically polarizing filter, right? So if we put and then let's call the 0 state, let's call that vertical. Why not? And let's call, or actually, I guess it's better to do, we'll call that 0 horizontal here, right? And then we'll call that 1 state vertically polarized, right? So we can think of, if we have something in the 0 state, right? This is just a generalization, but we're thinking about that state in this case as a photon that is horizontally polarized, right? And then this 1 state, we're thinking of a photon that's vertically polarized, right? So if we pass a photon in one of these states through this filter, right, we're gonna know whether it's horizontally or vertically polarized. But this state, for example, so this is the plus and minus state. So these are the diagonal states. So we could say maybe diagonal and anti-diagonal, right? If we put something that's diagonal or anti-diagonal through this filter right here, right, this vertically polarizing filter here, we're not going to get any information about it. So let's look at this diagram with that in mind, right? So basically how this BB84 protocol works, right? Let's say I'm Alice and I want to, I want to prepare a set of photons for Bob, who I'm trying to communicate with, right? We'll do the simplest possible version of this. So what I'm going to do is I'm going to prepare a bunch of photons in the diagonally polarized state, right? So this is the X basis, right? So we have, this is, let's say we were saying this is anti-diagonal, right? So, or this is diagonal, right? Diagonal, diagonal, anti-diagonal, anti-diagonal, right? And then we're also preparing stuff in the Z basis, right? So we have, let's say we're saying 0 is horizontal, right? So we have horizontal, vertical, vertical, right? So I go ahead. So Alice goes ahead and she sends those qubits to Bob, right? So what Bob is going to do is he's going to pick a random set of bases to measure those in. So let's say here he picks X, so he picks right, right? So he gets the correct result here, right? What about the second time? He picks wrong, right? So remember what we were saying. We have something in the horizontally polarized state. We measure it in the diagonal basis, right? We put it through a diagonally polarizing filter. It destroys all the information. So Bob doesn't know what this qubit is, right? Now, what about this one? Well, this one Bob measured in the correct basis, right? This one was vertically polarized. He put it through a polarizing filter, vertically polarizing filter. He got his correct result, right? So every time that Bob happens to choose the same basis as Alice, right, he's going to get the correct result. And the crazy thing about this is that as long as Bob can verify that he has the correct string of qubits, and that no one intercepted those qubits or did anything to them, and that he actually is in physical possession of them, I guess that doesn't even matter, right? So let's say Bob goes and measures those qubits. What Bob and Alice will do is they'll do a correlation check, right? So they'll pick a few random ones and see if they correlate. If the correlation is below a certain amount, then they know that there was something happened, right? So if someone goes and eavesdrops and makes all these measurements, right, does what Bob was doing, they're going to destroy half of the photons, right? So then if Bob goes and he makes some measurements and checks it with Alice, right? If let's say someone measured this one in the diagonal basis and destroyed it, right? Well, Bob's going to know that, right? Because he's going to get a incorrect result for this, or he's going to, get wrong results for these measurements here. So if they check their correlation, they're going to find out that someone was eavesdropping and made those measurements, right? So that's basically the gist of it. I hope that was illustrative enough for you guys. I try to break it down as much as I possibly could, but you see these four ones on the bottom where they happen to pick the correct basis, right? Where Bob happened to pick the same basis as Alice, right? He gets that information perfectly securely transmitted, right? So the idea is if you can transmit a photon, right, like in this way, then you can have perfectly secure communication, right? You have an encryption by the laws of physics that it makes it impossible, at least, if someone snoops in your information, it makes it actually destroys that information itself and makes it obvious to you that someone was making those measurements, right? So that's basically the gist of why quantum communication is so important, right? We're dealing with in the age of Edward Snowden, in the age of the U.S. government just getting totally hacked by Russia or whatever, right? In the age of all these crazy things that are happening with cybersecurity, it's becoming really, really important. That it's becoming really important that we can have this level of perfect security. So this is kind of review. If you guys attended Ishan's workshop, he went over a lot of this stuff. But I just wanted to go over it one more time in case you guys hadn't been to that workshop, because I think it makes everything we're about to talk about puts in a nice context, gives you guys an intuition for why this is so important. Why is it called BB84? Because it was there was a guy named Bennett Brassard in 1984 that published a paper that described this technique here. So I'm going to clear all my drawings, get rid of annotation. There we go. So we're also going to talk. So this is kind of just a general outline of what we're going to talk about today. We're going to talk about what quantum communication is. We're going to talk about some fiber optic experiments that are being done in this field in Argonne National Lab in the University of Chicago. We're going to talk about three-node quantum network and what that means, and a satellite that you might have heard of that has been launched by the Chinese government as well, called Mesius. And at the end, we'll talk about how a quantum internet would work. So the question is, what is quantum communication? So you might have heard of quantum computing. You might not have heard of quantum communication. These fields are they're similar, but they're not the same thing for sure. So um, basically, we're using quantum effects to secure and transmit information. So what I just showed you guys, that BB84 protocol, was an example of quantum communication, right? Um, and then quantum key distribution, which was a lot of what Ishan's workshop talked about last quarter. Um, that has the potential to, as we were talking about, right, provide unbreakable encryption, right? So prevent the things that happened to the U.S. government last year, right? Um, and then we would have basically a set of entangled quantum communication nodes. So we have, right, you see entangled photons in this diagram right here, right? So if I can take two photons, entangle them, send one to one person, the other one to another person, right? They can use those photons to communicate. Um, and then I guess just a distinction of the kind of difference between quantum communication and quantum computing. So quantum communication also makes use of qubits, which are the basic unit of quantum computing. And quantum computers themselves can be networked using quantum communication. However, when we're talking about quantum computing, we're talking about running algorithms. So we're talking about taking a bunch of qubits, entangling them in different ways, performing manipulations on them. We have some interference effect that is going to yield a result, right? And that interference effect makes use of the quantum wave function, right? Which is something that classical computers don't have access to. They just have access to ones and zeros, right? And then we get our result, and using those principles, right? Quantum communication, we're more dealing with you know sets of entangled pairs of photons, for example, right? We're dealing with storing quantum information and transmitting it to different, through nodes and through fiber optic cables or through a satellite or whatever, right? And actually, when I was first getting into quantum computing, I kept seeing like people, experts were saying, quantum communication might actually have the greater potential out of these technologies. And the Chinese government certainly thinks so. In fact, the Chinese government is pretty much exclusively, or at least 90% or something like that of their research is going towards quantum communication. And I think what a lot of people say is they got really scared when they started finding out about like what the NSA has been doing when Edward Snowden releases those documents, right? China kind of freaked out a little bit, and then they started investing in this technology. And it is very, very, very possible that we could have full quantum internet at some point in the next couple decades. So that's really exciting. That would provide, basically perfect security by the laws of physics. So that's the kind of the gist of it. So we're going to get into the first. So there's kind of two technologies we're going to be talking about. First one is fiber optics. So we're moving photons, entangled photons, quantum photons along these fiber optic channels, right? The second one we're going to be talking about is the satellite communication, that the research that China is doing. So first, we're going to talk about fiber optics, and Thomas is going to give you guys some background on the experiment at the Argonne National Laboratory that's been ongoing for a few years now.
Yeah, so the actual experiment that Argonne later published and talked about was performed on February 11th, 2020. It involved a 52-mile fiber optic loop. It was 26 miles from Argonne National Lab to University of Chicago, and then a 26-mile track back. And essentially, what they did is they sent out entangled photons on this track. They actually had two tracks basically, and they sent them out through the track to the University of Chicago, and then got them back, and then tested to see if they were still entangled. And essentially, the point of doing this is, it's one thing to say that you have entangled particles when you're in a lab and they're right next to each other and you can keep everything the same temperature. And it's another thing to test for entanglement when you have these fiber optic cables that are running under highways, as well as just the thermal expansion and contraction due to varying temperatures. So if you go to the next slide. So this is just basically a graphic of what they did. So they just sent entangled photons from argon over to University of Chicago and then back again. And then can you go to the next slide? Yeah, so the correlation, or like the entanglement of the photons was measured with a high signal to noise ratio. Basically, it was like measured with pretty high confidence. And this experiment just sort of served as a proof of concept that fiber optics could work in the real world to send entangled information. And right now, the latest that we've heard is in July of 2020, they basically announced that they're working with Fermilab to establish a 3-node quantum network. And it's going to be like an 82-mile loop. And to talk about 3-node quantum networks, I will hand it off to Matthew.
Yep. And so you might wonder, like, okay, 3 nodes, like, why is that important? Like, why 3? Like, what's the big deal here? And basically, the deal is that it's really hard. So essentially, when we entangle 2 qubits, it takes some time. The probability of entanglement occurring the way that we want it to, like actually happening, is pretty low. And so usually with 2 qubits, like it takes a couple tries to get an actual good entanglement formed. And so as you'd expect, if you like increase the number of qubits, if you try to go up to 3 qubits, then the probability of getting that to happen is even lower. And so it's even harder. And that means you need to have even higher quality equipment, and you need to have even higher quality states and better entanglement and better everything. Yeah, and that's really some of the basic challenges, is scaling up the quality of your qubits and your fibers and your coherence and everything else so that you can entangle more and more qubits. Because in order to form a really large and successful network, you'll actually need to do tons of entanglement operations all the time. And eventually, some of the goals that we've mentioned for a quantum internet include quantum key distribution and that kind of cybersecurity kind of stuff. But also a second one would be distributed quantum computing. So essentially being able to do part of your computation somewhere and then send that quantum information somewhere else and do the rest of it somewhere else. And that requires tons of entanglement. And so entanglement is a big deal. And yeah, as Thomas mentioned, recently, a couple of researchers from the Netherlands, very recently, like in April of this year, published a paper on a 3-node quantum network. And the way that they did it is they used color centers in diamond. So as we've mentioned, in order to send qubits, you have to send them usually by light using photons in fiber optic cables. And so that sort of explains the first part, like, how do we actually connect to quantum computers? Well, you send you'll send optical signals. You send photons, or maybe like squeezed light states or something like that. Most often it's single photons. But the second thing you need for a quantum network is you need to store those states. You need them to stay there and not decohere. And this is like the biggest problem, even in quantum computing and everywhere, that your qubits constantly decohere, they just fall apart, noise ruins them. And so one of the best systems where you can actually not only transfer the qubits, but also store them is called a nitrogen vacancy center. It's a color center. And what you have is, here in this picture, you can kind of see, you have a diamond, and that diamond will have a hole in it. And that hole, it'll literally be like an atom-sized hole. It will be missing a carbon atom. And then usually there'll be like a nitrogen atom in there, which forms fewer bonds. And then there's kind of like a gap. And that gap can have a quantum property called spin. And that spin forms a qubit. That spin can store, your 0 or your 1 or your plus state or your minus state. And the beautiful thing about nitrogen vacancy centers is that they can store it for a really long time. Noise doesn't ruin it nearly as quickly as it does in all sorts of different qubit states. And so, and the other beautiful thing is that they can actually be coupled to light. So you can shoot a laser at, well, as a broad generalization, you can shoot a laser at your nitrogen vacancy center, and that will transfer the qubit from the laser to the diamond, to the hole in the diamond. And that's the beautiful thing, right? You can send qubits over an optical fiber, and then you can store them on your little diamond chip. And it's also really cool to me that you can just grow diamond in a lab, and that's what this gets used for. But anyway, it literally diamonds. But anyway, and okay, side note, nitrogen vacancy centers are what give diamonds their color. That's why they're called color centers. So if you've ever seen like a pink diamond, oftentimes pink diamonds literally have these tiny little holes. And the thing that makes the diamond pink is kind of magical in a sense. That is that nitrogen vacancy center, which can store a qubit and allow for quantum information processing. So anyway, what this paper did is they built quantum nitrogen vacancy centers. Yes, impurity makes them beautiful. You might not be perfect, but you're still beautiful. Yeah, these nitrogen vacancy centers in the diamond allow them to be entangled, and this using this pretty complex system of interferometers and lasers and beam splitters. And recently there was this demonstration of this technology that was exciting.
Sorry, 1 second.
And yeah, just a few quick points about what a quantum internet requires. You have to transfer the qubits over long distances optically and quickly. And that gives you, that's where fiber optics and photons come in. You need to store them for a long time. That's where nitrogen vacancy centers with their long coherence times are really good. And then you need to interface the optics with the qubit. And this is kind of a challenge. There's all sorts of like magnetic materials or like special properties that you need to use, or like resonance. This is a real like complicated field, but recently they were able to very successfully do this with color sample qubits.
All right, so I guess you're gonna talk about this one too. So this is also Matt's time to shine on this one.
Yep, and so actually some of you might have seen I shared the picture on quantum patents, which shows that China has a stupidly large number of quantum key distribution patents. And one of their papers, research papers that came out very recently, in January of this year, is about this massive quantum network. Specifically, it's a 4,600 kilometer long quantum network. When I read this research paper, it cracks me up, right? Because a lot of the time research papers are something along the lines of, oh, we made this material and it's cool, or, we proved this model works better than that model. But this research paper was, we built a quantum network that covers most of the big cities in our entire country, spans 4,600 kilometers, and is way more advanced than anything else that has been built up to this date. And then it's just some pictures and some explanation. But essentially what it is along that orange line, that's the quantum backbone. And essentially they built optical fiber links that are extremely fast for quantum by quantum standards. And it links major cities in China. So it links Beijing, Jinan, Hefei, and Shanghai. And then they also built a sort of free space optical system up in Xinglong, above Beijing, that communicates with a Mesius satellite, and also communicates over here. You can see to Nanshan, which is like really far away. It's tremendously far away. I think it's 2,600 kilometers away from Xinglong. And what essentially they've done is they have formed a network where any single point, any of those yellow dots, can be connected to any other yellow dot using a relatively secure quantum encrypted network. So they can generate a key between any 2 points along that orange line, and also with the blue square that you see in the top left up in Nanshan. And it's amazing. And then essentially what this uses is it uses some of those entanglement operations. So it uses entanglement swapping and similar properties. And actually one of the amazing things that I sort of learned about this network when I was reading about it is it uses the exact same protocol that Ben described earlier in this talk. That BB84 protocol is the exact same one that they're using on this quantum network, mostly because it's very quick and it's probably one of the simplest ones to implement. But going forward, they will switch to slightly cleverer ones that make them harder to hack, like the detectors and the sensors.
I actually didn't know some of this stuff, so that's actually really, really awesome. I can't believe they I didn't know it was that advanced. That's pretty nuts. We're falling behind China, I guess, in this one. Um, I was reading some article that was saying that basically once the Edward Snowden stuff came out, and they found out how profoundly the NSA is hacking everyone and tracking everything. They decided, okay, we're gonna do this quantum thing so that we don't have to deal with that. So um, that's kind of nuts. I love the NSA. Yes. If the NSA is listening, first of all, why are you listening to this? And second of all, we all love you too. It's always listening. It's like that meme with Billy and the FBI or whatever. Um, so, so it's a good transition because Matthew talked about Mesius at the end of this thing. So Mesius is a communication satellite that the Chinese government has deployed in low Earth orbit. And it has something like 15 different experiments aboard it, but the one we're going to talk about is the one that is it's most known for, which is the hardware to distribute pairs of entangled photons. So the reason that you can't do this, you can't send entangled photons through the airwaves from a spot on the ground to another spot on the ground, right? Is because we have all these effects like scattering from the atmosphere, right? We're sending stuff diagonally through the atmosphere. It's scatters off the ozone layer. We're gonna we have the Earth itself is curved, right? So if you're trying to the same reason that FM radio only goes a certain distance is the same reason that we can't really do this without a satellite. So if we want to create entangled photons and distribute them, there's basically there's basically three ways to do it. Way number one is we can literally put one of the photons on a truck, drive it somewhere, and actually physically move it to another lab, right? And then way number two is if we have and not just any optical fiber, we have to have really some of the highest purity optical fibers that we can possibly access. This is kind of what the U.S. government is doing in Argonne, right? And then way number three is we can actually give a satellite the technology. So this is Mesius or Tiangong 2, right? We can actually give a satellite the technology to create a pair of entangled photons and distribute those to actual ground stations using it's a type of interferometer. I'm not as familiar with it, but basically it creates those two entangled photons and distributes it to ground stations or labs in the ground. And so I'm going to talk about a little bit about the E91 quantum key distribution protocol. Not as in depth as last time, but I think it's the most straightforward intuition on why having a pair of entangled photons can help you communicate better. And then they were actually able to create a secure quantum channel between China. They did an international experiment with researchers in Vienna, Austria. So I think it's something like over 4,000 miles total of channels that they had to use in order to make this work. And they actually were able to keep these photons entangled, which is just absolutely nuts. So really, really crazy stuff that the Chinese government is doing. And so I guess I'll just briefly kind of talk about E91 quantum key distribution. So the thing about entangled photons or whatever entangled quantum particles that you're talking about is that their measurements are correlated, right? So we can talk about these are called Bell states, and these are states we can put two photons in where there is 100% chance that you will either get both photons measured, let's say horizontally polarized, or both photons measured vertically polarized, right? There's 100% chance, 100% correlation between measurements. And then I'm sure many of you have kind of heard about a little bit about this, right? There's the classic, spooky action at a distance. It's a very counterintuitive thing, right? If I go and I measure my quantum state or whatever, right? And then let's say I give Matthew another entangled photon and he, flies to Mars or something like that, right? If I measure my quantum state, if he goes and he measures his, he's going to get the same result as me or a 100% correlated result with me without us even communicating and faster than the speed of light, right? Very, very strange result. But what that lets you do, you could just maybe think about this as a thought experiment. If I had the ability to generate completely random numbers, and I also had the ability to generate those random numbers for only one other person, right? So let's say I can generate a random string of numbers, and then Matthew, for example, I magically give him the ability to generate that same random string of numbers, right? Exactly, right? Um, so think about how useful that would be for cryptography, right? You can imagine that would make a lot of the protocols we use for cryptography kind of obsolete, right? If we had the ability to create perfectly correlated, randomly generated strings of numbers, right? That would completely revolutionize the field of cryptography, right? So that's basically what the E91 protocol is, right? It's using pairs of entangled photons to encode information and to basically it's so in regular cryptography we have either a private or a public key. This one is kind of neither. It's a private key that we both have and that no one else has, right? So and it can't be eavesdrops on, right? Like let's say I make all my measurements, and then Matthew makes all his measurements. We take a random subset of those measurements, not enough of them to have to have anyone be able to deduce any information from what we send, right? But let's say I send Matthew, a random subset of my measurements, and he sends me a random subset of his measurements, right? We should be able to deduce whether or not someone was tampering with those measurements, right? Like let's say someone else, measured that photon and then, gave Matthew, a new photon or something like that, right? Then the correlation between me and Matthew's measurements are going to be off, right? We're going to lose that correlation there, so you can't be eavesdrops on. So that is something, as you can kind of I feel like you could probably just imagine that, right? How revolutionary it would be for cryptography if everyone in the world could generate a random set of numbers and have that be perfectly correlated with another random set of numbers that someone else somewhere anywhere else in the world could generate, right? You pretty much would not need a lot of the protocols like RSA that we use for cryptography. So that's really exciting stuff. Really, really kind of nuts research, actually, in my opinion. The fact that they've been able to do this, create two entangled photons and send them to two different places and have them remain entangled, 4,000 miles away between Vienna and China, is just kind of unreal, to be honest. And then let's see. I think Matt's going to talk about kind of the limitations of this experiment and why it isn't fully there yet.
Yeah. And so, those of you in cybersecurity, you should not worry, because quantum key distribution does not destroy your field or invalidate it in any way. In fact, it actually makes it much more interesting. And one of the reasons is that, sure, you can't actually hack the link itself. So the way that we used to break encryption and steal people's secrets is, for instance, during World War II, we would tap Nazi communications, and then we would just record all of this cipher code, and then we would run like really advanced computations on them to decode it. So with the Enigma, we would just record information, whether it was sent by radio or by telephone line, and then we would actually do like a ton of math on it and like really clever modular arithmetic and that kind of thing to figure it out. And quantum key distribution means that you can't do that anymore. You literally cannot just tap a line and take the information and then run tons of computations on it. And right now it's really hard to do that. Hypothetically, you could if you wanted to do that, with, for instance, RSA, it's very difficult. It's very computationally intensive. This is one of the reasons why people build supercomputers, is to crack other people's encryption. But it's really challenging. And as we mentioned before, quantum computers might help with cracking people's encryption. But QKD destroys this possibility for you. You can't just tap a line and then decrypt it. But you can still hack a million other things. For instance, you can't hack the line itself, but you can hack the detectors that the people are using to detect the photons. And you can hack the light sources. And there's a ton of really clever other attacks you can do. So for instance, suppose somebody sends a single, instead of sending one photon the way that they're supposed to, suppose Ben accidentally sends two, because among other things, building a perfect single photon source is really difficult. Well, what I can do is I can split those photons. I can take, if Ben is trying to communicate with Thomas, I can actually, and he accidentally sends two photons, I can actually take one of them, give the other one to Thomas. Ben creates his magical key with Thomas, but I have another photon that is entangled with those two, and I can figure out what their key is. So there are like tons of really clever ways to do this. And although the link is theoretically perfectly secure, first of all, you have to actually create a perfect link for that. And second of all, you can hack tons of other things. You can hack the detectors, you can hack, the lasers. If there's a trusted node in between, you can hack that node. And so there are quite a few challenges remaining to implementing really secure systems. So one of them, for instance, is that as I mentioned before, Ben talked about the E91 protocol, which is used for the free space optical satellite component of the QKD. That is more secure, but along the optical fiber link in China's experiment, they're using BB84, and BB84 is actually not that secure, because hypothetically, if someone can hack the detector, then anyone with access to the detector, so for instance, if I hack Thomas's detector classically, and I just give myself those results, then essentially I can figure out what their code is. And so there are all sorts of more complicated algorithms that require more photons and more time and higher quality, like entanglement or superposition, to generate, that counter this, that are called like measurement device independent protocols. And there's like a whole science built around this. And so although quantum key distribution fundamentally changes the landscape, it doesn't destroy cybersecurity. In fact, there's a whole new sort of field of cybersecurity of, okay, sure, if they did their job right, if they built their quantum key distribution network correctly, then we can't hack it. But did they make a mistake somewhere? And also, can we hack their electronics? Can we hack their computers, and so on and so forth? So yeah, it's a really interesting field, and it will take some work.
Mm-hmm. So, and I guess we'll just real quick, we're gonna do a few hot takes of some other quantum communication ventures that are happening right now. So, there is a quantum internet alliance in Europe, which is part of Europe's the kind of pan-European big quantum initiative in general, that is, it incorporates quantum internet and quantum computing and a couple other things. So they're starting to really, they're trying to get it to the next stage, and really kickstart this project. So we'll see what happens with that. And then also, NASA announced the development of the National Space Quantum Laboratory a couple years ago, which is supposed to be a module for the International Space Station, that can be used to do basic research on quantum communication and quantum internet. So that's kind of exciting. I know I guess we're still a little behind China, but hopefully if we can make that work, then we can maybe catch up a little bit. And also the thing about the U.S. government is, a lot of stuff goes on behind the scenes. Is classified. So this stuff is stuff that is not classified that we know about. The U.S. government, maybe whatever branch would be responsible for that, may have been doing research on this for 5 years, and we just wouldn't know. Maybe it's classified. There's also a company called QFOX, and they're developing what they call a quantum router. And it purports to be able to allow quantum computers to communicate with each other. And they make a very bold claim. They say, if it's really hard to get 1,000 qubits, but if I have 100 qubit quantum computer, a quantum modem, or a quantum router, another 100 qubit quantum computer, quantum router, that somehow you can daisy chain that into 1,000 qubits. I'm not sure if that's true, or if that even is possible with the laws of physics, because you do have to have every single photon entangled with most of the other photons in this situation. It's not the kind of thing where you can have one link. So you might have to, if you have 100 qubits, you might have to have a few dozen links between those two labs in that router. So I'm not sure if this would work, but they make a very bold claim, and it got a lot of hype. So we'll see. The people that are involved with it are definitely very smart people, physics PhDs from the local university. So we'll see what happens with that. And then in 2018, the U.S. government passed the National Quantum Initiative Act, which should be, if you guys are thinking about getting into this field, that should be very interesting to you because there's a lot of grant money, a lot of financial aid and scholarships available for people who, if you want to get go into higher or get a PhD or a master's degree. There looks like there's going to be a lot of stuff that's going to become available pretty soon here once this money starts moving around, and then there's just going to be a lot more positions and labs, a lot more kind of private and government partnerships to do like the way that Argonne National Laboratory partnered up with the University of Chicago. Be a lot more of that kind of stuff. So if this is possibly a really good time to get into this field because of this Quantum Initiative Act. But it also increased funding for quantum communication ventures in the U.S. By I think a few millions of dollars. So I think I'm not sure. I want to say that Argonne lab stuff is probably money from this Quantum Initiative Act, but I'm actually not sure. If it isn't, it will be soon. And Argonne National Lab is going to be getting a lot of money pretty soon from this act. So we'll see what happens with that. It's a good thing to keep our eyes on. So, and then the last thing we're going to talk about is kind of how a quantum internet would work. So I think Matt was going to talk about this slide, this crazy picture that I'm not even sure I understand. So go ahead.
Yeah, so if you can see that diagram kind of there, it's got quite a few layers, an application layer, classical logical layer, classical physical layer, quantum logical layer, and quantum physical layer. And that picture is describing how yes, onions have layers, ogres have layers. And that picture is describing how the current quantum system in China, that was based on that big sort of backbone, is working. And it's actually working today, although somewhat slowly. And so one good thing sort of to cover first is that there are kind of two levels of quantum internet. The first level is what we see here, what China is doing now, and both of them are very important. And the first level is just being able to form QKD links, being able to do quantum key distribution really efficiently across tons of different locations and tons of different cities. And that's what this system does. And then the next level up, once you have, a multi-qubit entanglement, for instance, that 3-qubit entanglement goes up to 4 and 5 and way more. And once you have really high quality links, then the next level up will be actually like distributed quantum computing and like sharing qubits, sending other people in other labs your qubits, and even all sorts of really complicated and really cool stuff that I don't understand. Like one idea is that actually if you're doing astronomy and you have measurements of like astronomical measurements, then if you have a quantum network that connects to telescopes, then eventually using a quantum network, you could actually understand more of that data, because some of that data will consist of entangled light. And so if you have a quantum network, you can process that entangled light. Don't ask me too many questions about that, because I don't understand it very well, but it's really cool. And so the quantum internet that exists today is this system that you see in that picture. And essentially what it is it's the regular classical internet, except it has this quantum layer that enables really efficient quantum key distribution for secure communications. And essentially what happens is that, in our pictures, they're kind of on the left, for instance, a banker or somebody who needs a secure link in Beijing will send a message to their classical logical layer and say, I need a key. I need a key to connect to my buddy at the bank in Shanghai. And if the quantum network is always on, it's always generating new keys. And so if they have a key, they'll just give it to them. If they don't, then they'll request a key. And if a key hasn't been generated, then we go down to the quantum logical layer, where we essentially generate a new key. And the way that works is we go through the whole, at this point, the whole BB84 protocol that Ben described. So, then they'll contact the trusted node in Beijing. So the user in the bank will actually connect Classically, I think, I'm pretty sure it's classically connect to the nearest trusted sort of server or like system in Beijing. And that system will actually perform the quantum key distribution algorithm with Shanghai. And specifically, the way that it will do it is it will actually perform quantum key distribution with a closer node, and then it'll do entanglement swapping, and then do quantum key distribution with the Shanghai node, and then eventually it'll get back that key. And then once we've done that on the quantum physical layer, on the quantum logical layer, that corresponds to generating a key. That key gets sent back up to the classical logical layer. So basically we say, okay, we've got this number, it's your key, use this here. And then now that both users have this, then they can actually do their entanglement protocol. And so one of the things that you can see that's cool about this diagram is you can see that it's not end to end. It's not like the guy in Beijing has a literal a photon source and a detector, and then he goes beep, and he's like literally doing that. No, there's actually quite a few classical layers in between, and that means that you can hack those classical layers. And then the second thing is that, yeah, they did mention in the paper that if there is a high priority user, then the high priority user will be able to bypass some of those classical layers. So the high priority layer will be, user will be able to do direct end-to-end entanglement between Beijing and Shanghai. But the much faster way is to use intermediate nodes and entanglement swapping, which is faster but less efficient. And so, yeah, once again, we see that the sort of really perfect, really intimidating, really good keys will be used for the most secure tasks, like really, really secretive stuff. And then other stuff will still be much harder to deal with than classical, but it will have all sorts of vulnerabilities in there that hopefully people like Ishan can exploit.
Mm-hmm. And then, and then I guess we'll just kind of wrap it up talking about basically what is this going to look like? What Matthew described was like, fully fledged network, and all the infrastructure is already in place there, right? But as of now, obviously we don't have any of that, or at least a lot of that stuff, that physics hardware and interferometers and all that stuff in place. So I think a good analog is the Arpanet. So if you guys have heard of the Arpanet, it is the origin of the internet. The internet before it was the internet. So it was basically just government government nodes, right? And then academia basically was kind of the first layer that it's kind of spread to, right? And then kind of haphazardly started growing and adding new nodes, new terminals, and everything, and kind of eventually became the internet as we know it. The U.S. is planning on taking kind of a more careful approach this time. Than they're trying to learn from their from how they did the ARPANET. And they're trying to make it a lot more structured. So they're going to try and connect 17 national laboratories with fiber optic quantum loops, so that they can basically connect them all as kind of nodes of a quantum network. And then eventually, from those laboratories, they're going to expand that to the rest of the country. So I guess what Matt's talking about with having all that classical support software there and systems could possibly work in a similar way, right? The actual quantum hardware could be done by these laboratories, and then there could be support software and support computing being done over the cloud, so that you can connect to that laboratory itself, right? So we'll see what happens with this, and in the real world, what an actual quantum internet would look like would not just be what the Argon experiment was, which was fiber optic nodes and fiber optic cables. It also would not be what China was doing, because I think even if you figure the technology out, you still have to deal with, I think the satellite can't be in direct sunlight. It's there's a lot of issues with noise, with if it's raining or if there's atmospheric interference. There's a lot of stuff you have to deal with. So what most people think is some combination of those two, right? Of quantum satellites and quantum fiber optic channels is going to be involved in this project. We don't really know if if this would be international or if it would, it's certainly possible that Europe and the U.S. and China would have, their own quantum internets. So it might be kind of unlike the World Wide Web that we have now, where it might be a lot more localized. But we'll see. China has collaborated with European researchers, for example. So we'll see what happens with that. It's kind of exciting. It's kind of in its infancy. It's like I don't know, maybe what was it, the 80s, I guess, in real internet. Was that kind of about where we are now in quantum internet? So really exciting stuff. Who knows if it's gonna be if we could wind up had just encryption could just get better. We never know, and we might not need all this stuff, but we very well could have a quantum internet in a couple decades. So we'll see. It's kind of exciting stuff. I think Matthew was going to say something too.
Yeah, one thing we can actually bet on is that sooner or later, we're going to get a quantum network node at UCSD. In a couple, I didn't hear this from Kosla. I didn't talk to him or something, but in a couple, at least in a couple decades or something, the most likely scenario is that SDSC, the San Diego Supercomputer Center will get a QPU, like a quantum processing unit, and they will probably build the sort of connect into a quantum network with the rest of the supercomputing centers. Rest in peace. And actually, classically, we already have this. So one of the things that I sort of found interesting when I was reading about SDSC on campus is that besides like the internet that we're all connected to, supercomputer centers always have these really high bandwidth, really, really fast networks that just connect one supercomputer center to another, so that if you want to do something on both, you can send your absolutely massive files super quickly. So we already have like extremely fast links to other supercomputer centers across the country and other national labs and so on. And in the future, we'll have a similar thing with quantum networks connecting, as Ben mentioned, different labs across the country.
And I think that concludes it. So we'll open it up for a second if you guys have any questions. I know this was a lot of stuff. It might be the kind of thing where in your normal classes where the professor goes over some crazy stuff and then you don't even know what to ask. So it's all good if you guys don't have questions. But if you have anything you're curious about, Matthew and I will try our best to answer it for you. But you guys might be oh yeah, and then real quick, we also have a Google form too for you guys if you guys are interested. So we're trying to just get more feedback in general from this workshop. And then wait, oh, I have to. I'm screen sharing. So if one of you guys would be able to share that real quick, that'd be awesome. Because we'd like to just get some feedback from you guys. Awesome, Andy just sent it there. So if you guys don't mind filling that out, if you're interested, that would be awesome. But thank you everyone for coming. We really appreciate it. It's I understand the Zoom fatigue is real, so I really appreciate you guys coming out. And I think I think we went over some really interesting stuff today. So this is actually personally some of my favorite content that we've presented through this club. So appreciate you guys coming out, and hope that it was interesting and that you maybe learned a few things, and hopefully didn't go over your head too much. We try to keep it nice and simple, and as straightforward as we could. So take care, everyone. Bye Chase. Bye everyone who's gonna head out. And then if you guys want to stick around, we'll probably hang out for like a couple minutes. And then I guess the last slide, if you guys, I think everyone on here is like pretty much on our Discord. But if you aren't, you can join our Discord community. I guess let's see. I have to let me stop the share so I can send you guys a link in case there's anyone that's not on there. Oh, I'm still recording. Thank you, Yushan. Gotta work on my Zoom skills. All right, so I'm gonna stop the recording.